Okay, now we're going to talk about the hydrologic soil group, the curve number, and the time of concentration. So to figure out where the soils are, let's say a lot of times we don't have the geotechnical information right away. The soils group from the NRCS website are actually pretty good for us to start our designs on, so we don't have to wait for the geotech. Go to the website, type in the 1007 Votaw Road on this, and we did this homework assignment last time, and you're going to find out for our project site there's two different types of soils. There's going to be the Tavares and the Candler. They're both soil type A, which is really good for us. So go ahead and click on the link and search that data, because you will be adding that to your report. Now the second thing that we're going to talk about is the curve number. Curve number is actually related to the soil type, and it's related to what type of land cover is. You can see in this aerial picture that our land cover is actually trees. There's a house in there, and there's a dirt road, and there's a track, but the majority of it's forested area. So when we look at the NRCS TR55, Urban Hydrology for Small Watersheds, we have this table 2-2C. If you look at it, you go to woods, grass combination, hardland or tree farm, and you've got woods. I would go with woods. So you've got, well, maybe orchard, depends on what it was originally. It could have been an orchard farm, especially here in Florida, or some type of tree farm. So one of these two. So we don't know whether the ground cover is, or the hydraulic condition is poor, fair, or good. In either one of these, I usually use the middle ground, and I say it's going to be fair. We know that it's an A soil group, so it's either going to be a 43 or a 36. We can take a look, and if you're conservative, go ahead and use the 36. If you want a truer meaning of it, then you'll have to do a site visit, and you'll converse on what woods grass combination means. I would go with good woods grass combination because it's not straight up a forest. You can see there's ground cover and there is grass once you go out to the field site. You also have what poor, fair, and good condition means based on the ground cover, how much of the ground is covered by grass. And again, I would use the fair condition unless you do a site analysis. So we're going to go with the curve number of 43. Now, the next thing I do want to go over is the time of concentration. The time of concentration is, again, the TR55. We're going to look at the overland flow, which we have a required Manning's roughness coefficient. There is an equation. We'll take a look at we looked at the NRCS worksheet. We're going to create our own worksheets for this semester for all of these calculations, so you get familiar with the Excel program and how to write these formulas in, because the sheets themselves only allow you a certain amount of range, and I want you all to be able to calculate these values without just having to keep reprinting sheets. So we have overland flow, overland sheet flow, and we have shallow concentrated flow. So overland flow is usually about your first 50 to 300 feet. The NRCS web model only allows you to have 50 feet. So the P2, remember, is precipitation based on a 2-hour event. And then we're going to go shallow concentrated flow, which means it's either going to go over grass or asphalt, or paved or unpaved. And then we'll plug in the average slope of the ground based on whether it's paved or unpaved to figure out the velocity, and then we'll use the equation to solve for the travel time. The last part is going to be the channel flow, and the channel is based on what cross-sectional area of the channel you're talking about. It's based on the length of the channel itself. So we have the Manning's velocity equation here. We have to look up a Manning's N for the site. I've actually given you a couple links online to figure out what the Manning's N will be for a channel, and we'll go over the Manning's equation even more when we talk about open channel flow. So we're going to assume stream flow or bank flow stage. You can also use a depth based on the area of the channel divided by the top width and get a mean depth, and use the mean depth for your calculations, because you have to know depth to figure out the velocity in the channel. So we're going to look at it with respect to 1.49 times the hydraulic radius to the 2/3 power, slope to the 1/2 power, divided by the Manning's N. Now, once we get all of that data, we're going to to figure out where our first part of our overland flow is. And if you take a look at, see if I don't trip over all these cords. If you take a look up here, I've got 87.27 and 87.19, and I believe that was a 50-foot slope. That, or 50-foot distance, that gives me my slope of that first section. And then the green section is going to become my shallow concentrated flow, and we're going from an 87 down to an 83 at a certain distance. So we'll have to figure out the slope of each of those sections. Now here's the other thing, is this is the green section is overland, is shallow concentrated flow, and the blue section is also shallow concentrated flow. The reason I split them up in two is because you can see the contours are wider or further apart here, and these are a little bit narrower together. That means this is a steeper slope through here than it is at the top. So I wanted to account for the variation in slope. Because of the variation in slope, we'll get a different travel time in that section. And we also assume in this, there's not actually a defined channel. So I'm going to go over this on how to put it in Excel. So that'll be a homework assignment. So you'll work with me in Excel to figure this out. I like the sheets, but I also want the functionality to add additional segments if I need to. Okay? Now, I'm going to go ahead and pause here, and then we're going to take a look at runoff and the graphical peak discharge method.